Morning. So how are you today, this morning?
Just woke up.
Yeah, I remember the student life. I used to be a night owl, and somehow along the ways I turned into a morning person. So yeah, it's always a good idea. And thank you for doing that. Well, I'll go ahead and open up in prayer. I know a few more folks will be coming, and we have some folks online. So as always, for folks online, you can just do a comm check, or feel free to, if you have any questions, or use a chat. I'll go and open this up in prayer and give you a little sense of what we'll cover today. So, dear Heavenly Father, Lord, I pray that you would be working in the lives of each of the students in this course. Lord, I pray that the material will be clear, that it will be enjoyable, and that you would see how all of this material is going to be helping them in their future field of choice, what particular company or area. Also pray that you would help them with their spiritual formation, Lord. The papers that they're doing, the things that they're looking at in terms of understanding the biblical narrative, the theological concepts in which we live our life by, and pray that you would give them interesting and creative ways for faith integration in their future. In Jesus' precious name we pray. Amen. Well, I wanted to say again, thank you for those that filled out the survey. I've been starting to go over that in a little bit more detail. I think by now, I've got a good complement of responses. Of course, it's optional. I don't want to make anybody feel like they have to, but it's a way for me to get some perspective on how things are going. So at a time when I can actually make any vector checks as we go forward with the material. And over the next couple of weeks, I'll try and introduce a couple of things that I'm starting to observe. I know that we do have a range of students where people are at, as well as interest areas. And so I try and keep it interesting and also helpful for a variety of folks as best I can on that front. So what we're going to be talking about today is the last of the second major section, which is the operating system support. And this is going to be starting to look at it from a different point of view of how we're going to be leveraging all of these things in actually doing real stuff, what a computer is meant to do. And so that will be the bulk of what we're going to talk about. And so what I think I'm going to try and do is go a little bit more in detail in this. Some folks were asking for more detail. And so I'll do that for that. And also, if anybody is having problem with, say, one of your projects, David was gracious enough to come by my office and we were troubleshooting his Arduino kit. We got that to work. Josiah last Thursday was giving me a heads up that we were thinking that he should be using an Arduino Uno, and it actually was a slightly different device. And so we'll be talking about this more on Thursdays, that if you look at the menu for the various types of units that you can actually pick, Arduino Uno is just one of very many. And so there is a chance, depending on which one that you actually picked up, that it might be something different. And so if anybody hasn't actually turned that on, if you want to be doing that, come on by. If you want to open it up now or some other time, we'll be glad to give you some heads up on that. So let's go ahead and get into the chapter. And we'll be going over operating system support. And so basically, we're going to be thinking about how the operating system now engages. We've been talking about the elements of von Neumann architecture. By now, I think you remember all of those things. And so now we're going to be thinking about how that actually is used in real life. And so we'll be talking about, first of all, give an operating system overview, think about the operating system objectives and functions, think about the types of operating systems. And so I think most of you have familiarity with at least Mac OS or Windows. Probably some of you, at least to a certain degree, have been playing with Linux. And so they're going to be talking about two types of operating systems, and I'll offer a third one that maybe you hadn't thought about. We'll talk about scheduling. So basically, how does this operating system, it's actually one of the key elements to start to figure out what is going to be done when and with what resources. We'll be talking a little bit about memory management for the two main architectures that we're addressing, the x86 architecture, the Intel x86, as well as the ARM architecture. And we'll get an introduction to various memory management techniques of how you can be having efficient utilization of the resources that you have available on your computer. So especially with your Arduino kit, you're going to be seeing more of the cyber physical parts that come together. So there's the hardware, the memory, the I/O, that all has to come together. Stalling makes a separate category, the system interconnects. And then we have how you have the intersections with that, where we then start to work with the actual software. And so that will be the thing that we're going to be talking about mostly in this chapter. So we'll be focusing on the operating system, but there's other things that it leverages and hooks together when needed, having if there's any libraries or utilities, and then finally having the application, which is what the user is going to be seeing the majority of the time. So what are the services that the operating system does? And so if you ever look at the processes that are running on your computer, sometimes it can be a little bit tricky to figure out what is what. With Linux, it's a little bit easier. You can see what has admin rights or root access versus a user access. And so the operating system services are the most important system program. If this, the way modern computing is done, if this isn't there, it's just not going to work. It masks the details of the hardware from the programmer and provides the programmer with a convenient interface for using the system. And here are the kind of things that are provided, the program creation. Okay, I'm ready to do something. So you want to be starting Word or whatever program that you're using. It then manages a program execution. It's not, can be a dynamic set of resources that are necessary. It provides access to I/O devices. We started to be thinking about that a little bit when we were talking about various kinds of memory. And so an I/O device can be a keyboard or mouse, a monitor, all of those things. Or we also talked about Wi-Fi and Ethernet, all of these various things that you need access for the purpose of what your program is doing. You need to have controlled access to files. If you have access it, can someone else have access to it or not? Then there's the system access. Maybe this would be getting more into the privileged areas of not everybody would have access to system access. And Avery, I know you were talking about cybersecurity, and it just pops up a lot of different places. What a hacker is going to be looking for are where are there access points that he can find that nefariously that he shouldn't have. And so those are the things that you try and avoid. Finally, we talked about error detection and response. We talked about that shows up in a lot of different areas in the computing environment. And finally, accounting, you need to keep track of what's using what, when, and we'll get a chance to be seeing that from a couple of different points of view. So what are some of the interfaces that are key for a computer system, and the ones that the operating system has a chance to be part of? So you have the instruction set architecture. We mostly have been talking about the Intel x86 architecture, the ARM architecture. And so we're going to be doing our MIPS programming. So we're going to get a chance to have a little bit more insight into the ARM side of thing. And so we have that. We can also have application binary interfaces. Maybe you have some things that are proprietary, and not everybody needs to know how that works. And so just an executable is something. And so you need to bring those together, and the operating system is going to be helpful. The application programmable interfaces, the API, that would be the other area that would be something that would be there. So the operating system acts as a resource manager. So a computer is a set of resources for the movement, storage, and processing of data for the control for the control of these functions. The operating system is responsible for managing these resources. The operating system as a control mechanism is unusual in two respects. The operating system functions in the same way as an ordinary computer program. So it's just one of many, but it has special privileges. And the operating system frequently relinquishes control and must depend on the processor to allow it to regain control. And so it's a synergistic partnership. They're codependent on one another to continue to do the things that the operating system is designed to do. So we have various cartoons where we've shown the way that a computer system is. And so it needs to be thinking about resources. And so, okay, I'm going to be accessing parts of memory, different things that are there for input and output devices, I/O. And so these are the things that it now has to be in partnership with that. So in general, there's really two major operating systems that you'll be experiencing. I'll mention in a minute a third one. And so first one, the one that you're probably most familiar with, is interactive system. And so the user / programmer interacts directly with the computer to request the execution of a job or to perform a transaction. So you're on your laptop, your tablet, or something like that. This is the kind of environment that you would have. The user may, depending on the nature of the application, communicate with the computer during the execution of the job. So there may be some dialogue or ongoing back and forth. Another that is historical in one way, that you used to submit jobs to a mainframe computer, and so it's not interactive. So it has to have all that information that it needs so it can actually do that successfully. And that mainframe computer is going to be the one that determines when it's going to be executed, and will inform you when you're done processing that. I've had to work with mainframes in the past. Maybe a close corollary now is now thinking about the cloud, that you start to have instances of computing, but it still has a lot of the characteristics of an interactive system. A third type of system, it's what's called a real-time operating system. And for anybody that's aware of our CubeSat efforts that we're doing here, when you have something that's actually operating real, it has an immediate response. I've talked a little about the neuromorphic computing stuff that I'm doing. And that's another example. Is like when we're driving or whatever we're doing, we have to constantly be aware and responding. You don't want to have a lag time. If you had too much of a lag time, you're going to get in an accident. So when you have a satellite that's having to a lot of times operate autonomously because it doesn't get commands all the time, it's not always in the line of sight of where you can have that information sent and received, receiving commands and sending telemetry. So that's another category of an operating system that's available. So in very early systems, and I talked about the movie, The Imitation Game, Alan Turing, it gives you a nice idea. And so a lot of mechanical type of things that were part of the computer, but there really wasn't any operating system. So basically, the quote programmer is actually acting as the operating system, and so it's more clunky, it's more prone to errors. You may have seen what they did in the Imitation Game movie when they were trying to decrypt this code, this German Enigma code, and they had to put all these different dials because it had limited capability. And when they finally figured out that every message had Heil Hitler, and so that gave them a phrase that they could use the search space that they needed to crack that code. And so they would change the encryption key every day. And so that's one of the things that made it a lot more of a manageable problem that they could deal with. And so this is the kind of things that you would have, all of the scheduling, all the setup, all that was stuff that you would have to be doing. And as we've mentioned in a couple of different areas in the computing environment, we want to have efficiency and performance. Over time, people wanted more out of their computers, and this is the kind of direction that we would have to go. So this is just an illustration of a memory layout for a resonant computer. The early processors were very expensive, and therefore it was important to maximize processor utilization. So batch mode is one of the ways that they could be doing that. But still you have all these different things that maybe you still would have to have some interrupt that you would have. So, but basically you start to have this partitioning of what you're doing with resources to have things done in an appropriate manner. So we can consider the sequence from the point of view of a processor. At a certain point in time, the processor is executing instructions from the portion of main memory containing and so we saw this like here as an illustration of what that might look like. These instructions cause the next job to be read. And so there was something called job control language, JCL, and you can have things like this, things load, run, end. And so we're getting a little bit of exposure to these kind of concepts when we're doing our assembly language programming. So the monitor or batch OS is simply a computer program. We talked about that an operating system is just another example of a program. Well, what are some desirable hardware features that we would want to have? Memory protection. Avery with cybersecurity, maybe others that have interest in that. You don't want to have somebody overriding your memory and all of a sudden it's having you start to execute nefarious things, exposing things that are not there. So the user program must not alter the memory area containing the monitor. So this is the operating system. You don't want to override the operating system. That's going to give you the blue screen of death if you have a Windows machine. One of the things that could cause us. The processor hardware should detect an error and transfer control to the monitor. And so you think like the kernel, hey, something's going wrong. Can it recover or not? And the monitor aborts a job, prints an error message, and loads the next job. And so if you're able to parse it out, and so it's just a user error, you can say, I'm going to terminate this job, let them know what I can. That's going to be one thing. Privileged instructions, you can only be executed by the monitor. One of the strategies that was passed on to me, and I know you can do this in a Mac, and in Windows, I don't know if you can do this, but you can actually have like one has an administrator rights, one only has a user rights. And one of the strategies, a company I work for, that they said is make your day-to-day account that you use be a user account rather than administrative accounts. So it's just making it less vulnerable that people can get into the kernel and start to do some of those things that you don't want to do. An operating system is going to have privileged access. It's going to have privileged instructions, things that it can execute that others can't. And so that's true. Timer, it's used to prevent a job from monopolizing the system. If it takes too much resources, it could be interrupted and put on the side. You don't want to have something that's eating up all kinds of resources. Maybe it wasn't programmed very well and there's memory leaks and it's taking more and more of your RAM until you run out. And finally, interrupts. It gives the operating system more flexibility and relinquishing control and regaining control. And so some of the stuff that we'll talk about as we move towards the latter part of this lecture, we'll get a chance to be thinking about that. Well, now think about utilization. You might remember we talked about that reading and writing. It actually takes a lot longer than doing execution of instructions. And so here we see an example executing 100 instructions is done in 1 microsecond, while a read takes 15 microseconds and a write takes 1 microsecond. So therefore, if we want to talk about the percent CPU utilization, it's 1/31 or 3.2%. That's not a very good utilization. And what Stalling tries to do is give you a little bit of insight going into the kitchen, if you will, thinking about, well, how can we improve performance? And this just gives you an example. We'll be seeing this from a couple different points of view. So we have multiple programs, and so it takes maybe 1/10 of the time to do program A. Well, program B does the same. Well, if we combine those, now it could be up to 20% utilization versus 10%. And so, and if you have 3, then maybe it's 30%. And so this is a kind of strategy that we can be thinking about. Instead of single programming, we want to be doing multi-programming. So you can have program threads. Now we have cores. There's all these kind of things that are available. So I'll show a slide pictorially of this in 2 slides from now, but let's start to be looking at a couple jobs, and they have different characteristics. You can look over that if you like to think about that a little bit more. And now we can be thinking about, well, what is the effect on the resource utilization if we're doing it in a uni program, so we're only doing one at a time, versus we do it in a multi-programming fashion. And so maybe with those preliminary charts, seeing this might make a little bit more sense. So basically, we have like program 1, job 1, program 2, job 2, and job 3. You do one, and then you do the next, and you do the other. Well, what if we did it all at the same time? So now we're trying to go into this kind of a fashion where we're getting more efficient utilization of resources. So you can be thinking about the energy it took to do all of these are now scrunched into that amount of time. So that might be one of the things you have to be ensuring. But in terms of performance, this is going to get all 3 of those programs done at a lot faster time, roughly speaking, on the order of half the time. So that's actually be a good result. And so that would be one of the things that, just like we talked about caching in the past, maybe not intuitive, that caching and actually having an L1, L2, and L3 cache would actually make performance better. So thus we get into this idea of time sharing systems. It's used when the user interacts directly with the computer. Processor's time is shared among multiple users. So this would be more like a, if you're going back to a mainframe computer, or perhaps maybe you have something that you're at home and you have multiple people accessing your home server. Maybe that would be something where that might come up. So what are some of the ways that we can compare batch multi-programming versus time sharing? And so you give dedicated resources to one, or versus you just have multiple things that are available that can be using resources. Those are the 2 possible things that are there. There are a couple types of scheduling. And so long-term, medium-term, and short-term, and then there's IO scheduling. So long-term, it's a decision to add to the pool of processes to be executed. That would be for long-term, medium-term, the decision to add the number of processes that are partially or fully in main memory. And finally, for these 3, the short-term, the decision as to which available process will be executed by the processor. And then for IO scheduling, the decision as to which process pending IO request shall be handled by an available IO device. Since you guys have heard about my home saga, trying to get fiber optic installed, the latest edition that is I got this PCIe card, and that actually takes the Ethernet, and it's actually a card into, I have a Windows desktop computer that I have. I may show a little bit more details on Thursday. And so now it's faster, and this has to determine, okay, when am I getting bits that are meant for this computer versus some other resources? If I'm starting to make a query, this is an example of one of those IO scheduling. Am I going to actually do refresh the monitor, or am I going to service this Ethernet connection, which is now a lot faster? And so that's one of the judgment calls that has to be made by the operating system. Okay, so there's some more details about each one of these scheduling. I'm going to skip over some of the charts here, just due to time and just trying to focus on some things here. So we have the long-term. So the long-term schedule determines which programs are admitted to the system for processing. Then we get into the next ones. The medium-term scheduling is part of the swapping function described in section 9.3. So as you're reading the textbook, you can look over that. So typically the swapping in decision is based on the need to manage the degree of multi-programming. And we already mentioned the long-term, the short-term schedule, also known as a dispatcher, executes frequently and makes the fine-grained decision of which job to execute next. And so maybe, like this L1, L2, L3 cache, you could be seeing some kind of relatedness between each one of these scheduling that is actually taking place. So that's a strategy that gets into the architecture, the computer architecture, that you see is being leveraged in what we're talking about here. So let's talk about this process. And so if you go to your control panel and look up your processes, there's various ways you can do it on a Mac OS or Linux. And so you could be looking at what are the all active processes, how much resources are being utilized. And so you have an entry point of how you can have a new process coming in. You can, so it's either ready, and if it's ready, then it can actually be dispatched and actually run. And so this would be where you'd want. And then when it's finished, it releases those resources and it can go back, and the operating system can assign that to someone else. Or maybe it gets blocked, it's running, and it's taking too many resources. You need to give other people some of the computing resources. And so eventually, once the things are cleared out, and hopefully this is the way you would like, it goes back to a ready state, it can then go into the running. So this just gives you an idea. It's not like the fetch execute cycle, but this is getting into a little bit more surgical thinking in terms of what the operating system sees. I don't know, some of you guys, maybe you've already, or you may be taking it now, operating systems. I don't know how far along some of you guys are at. So that would be something that you guys are hitting. So for now, thinking of the process control block, for each process in the system, the OS must maintain information indicating the state of the process and the other information necessary for process execution. So you can think like it has its dashboard of stuff that it needs to make available. So the operating system can say, are things going okay? Is there anything I need to be concerned about? So this is something that would be like those dashboards of things that are shared. So this just gives you an idea. And so you can see the various resources that are laid out here. So to understand how the OS manages the scheduling of the various jobs in memory, we can begin by considering this simple example that we're showing here. So we're seeing the operating system for the state one, it's giving resources to program one. And so it's running, and then it finishes, then the operating system is in control. And now, well, actually in this case, it's not finished, but it's put into this waiting mode. And so the operating system then goes and gives access to program B for it to take resources. So this is the kind of thing that happens with a scheduler to, and so you can get a chance to get some perspective on that. So what are key elements of an operating system for multi-programming? I showed you that scrunched example. And so it needs to have those resources that it can be doing all these things. And there's a couple different strategies for doing scheduling. And we'll just touch on those lightly here. So in this picture, it's a simple example highlighting the basic functions of the short-term scheduler. It shows the major elements of the operating system involved in the multi-programming and scheduling of the process. Here is a queuing diagram representing of a processor scheduling. So once again, we're seeing some examples of this queue, these caching. Okay. So it's just how the processes progress through the computer under the control of the operating system. Each process request is placed in the long-term queue. As the resources become available, a process request becomes a process and is then placed in the ready state and put into the short-term queue. So those are the things that are actually taking place. The use of swapping, and so we discussed the three types of queues: the long-term queue request for new processes, the short-term queue for processes that are ready to use a processor, and the various IO queues of processes that are not ready to use a process. So this is just swapping can be one of the things that can be helpful for us for overall improvement of computing performance. So here's just an example of a fixed partitioning of a 64 megabyte memory. So this is a simple scheme for partitioning available memory is to use fixed size. So here we just see in 8 chunks, and here we're seeing it's varying sizes. And so maybe certain processes, you don't need as large of a chunk, so maybe it not be best use of the resources. So that's something that you can be thinking about. And so then we get into the effects of dynamic partitioning. So here we see 2 examples of fixed partitioning, one that they're all the same, one that there's different sizes that can be chosen from. And so we need to be thinking about how we're going to be allocating memory. Here we have 3 processes that are going, but all of these holes in the memory can't afford to do an additional process. And so that's where we can see that at the moment, for the way things are laid out, it can't handle any new processes. So Stalling then talks about both unequal fixed sizes and variable size partitions are inefficient in the use of a memory. Suppose, however, the memory is partitioned into equally fixed size chunks that are relatively small, and that each process is also divided into small fixed size chunks of some size. Then the chunks of a program known as pages, maybe you've heard that term in your operating system class, could be assigned to activate chunks of memory known as frames or pages of frames. So thus we have a couple layers of information stuff that we're starting to catalog. And this gives us a couple new strategies that we can be thinking about how we're going to best execute things, not just with fixed or variable partitioning, but having these frames, these pages, and all that types of stuff. Now suppose, as an example, that there are not sufficient unused contiguous frames for holding the process? Does this prevent the OS from loading A? The answer is no, because we can once again use the concept of a logical address A. Simply a simple base address will no longer suffice. And so maybe we can get a little bit more surgical of how we're going to be using that memory. And Stalling gets a chance to be talking about that here. Then we have this idea of virtual memory and putting that together with demand paging. With the use of paging, truly effective multi-programming systems came into being. So you can see how there is a lot of continual development and computing computer architectures and the implementations of that. And so each time we do a chapter, we can see yet another example of how, wow, people did research, they've done things in the lab, smart people figured stuff out, and then it's gradually now become part of the status quo, what people are used to doing. So the simple tactic of breaking a process into pages led to the development of another important concept, virtual memory. To understand virtual memory, we must add a refinement to the paging scheme just discussed. The refinement is demand paging, which simply means that each page of a process is brought in only when it is needed, that is on demand. And so this is what we get a chance to be thinking about. We have some pros and cons that we can be considering, and you can look over that in more detail to be thinking about that. An alternative approach to the use of 1 or 2 level paging tables is to use an inverted page table structure. And so this is something that I'm not going to get into too much detail, but this is now just taking it another step or two for what can actually take place. So in principle, then every virtual memory reference can cause 2 physical memory accesses, one to fetch an appropriate page table entry and one to fetch the desired data. Thus, a straightforward virtual memory scheme would have the effect of doubling the memory time, access time. To overcome this, the problem must, the most virtual memory schemes make use of a special cache for page table entries, usually called the translation look-aside buffer, TLB. And this is just giving an example of that. So it's really depending how far in the kitchen or under the hood, whatever analogy you want to be using for cooking or for automobiles, it just goes, you can go deeper and deeper, thinking there's been a lot of thought process, a lot of engineering that's been gone into this. And so now this is just another layer for that with this translation look-aside buffer and cache operation. Note that the virtual memory mechanism must interact with the cache system. And this is illustrated in this figure. A virtual address will generally be in the form of a page number offset. First, the memory system consults the TLB to see if the matching page table is present. So you have these things that are already accessed, put into a buffer, put into a cache. And so you don't have to go as far to dig for these things, and that can be a way of starting to improve performance. So we'll talk about a few things here, and then we'll start to wind up trying to think about at a high level how this impacts the architectures for the x86 and the ARM. So for segmentation, it's usually visible to the programmer, provides a convenience for organizing programs and data as a means for associating privilege and protection attributes with instructions and data. It allows the programmer to view memory as consisting of multiple address space or segments. And there's advantages and disadvantages, as typically we have discussed on different things. Okay, any comments or questions? That's a lot of information that I've spent probably 40 minutes talking about. Any observations or? You guys can give me feedback. I can keep having lectures that maybe are a little bit more detailed, or I can go back to maybe a little bit more of our greatest hits approach and give you a higher level way of thinking about it. So we have these two main areas that we are supporting in this class. And so how does the x86 do its memory management, thinking in terms of what it is going to allow, what it's going to facilitate for an operating system. So there's unsegmented page memory, unsegmented unpaged memory, unsegmented page memory, segmented unpaged memory, and segmented pages. And so we have like two variables. So we have like two to the two, so four possibilities, and we're seeing each one of these laid out here, what they have in their architecture. So unsegmented, unpaged, virtual address is the same as the physical address. Unsegmented page, the memory is viewed as a page linear address space. Segmented unpaged, the memory is viewed as a collection of logical addresses. And segmented page, the segmentation is used to define local memory partitions subject to access control and paging, et cetera, et cetera. So Unix system 5, so one of the precursors to what we have in Linux, tended to find this was something that was quite useful. Okay, we had our first chat on a little bit of segmentation, and then we have a little bit more. And so when segmentation is used, each virtual address consists of a 16-bit segment reference and a 32-bit offset. So this starts to get into some of the details of how they implement this architecture. And maybe I'll just put up this briefly, just to give you an idea of the kind of architecture that is out there. So the address translations mechanism for segmentation involves mapping a virtual address into what is referred to as a linear address. And there's just more details that you can be looking into. And this is just some of the acronyms that are used. And so you can see that. And so that's just finishing up for thinking about the x86 approach to memory management. There's also paging, but let me just skip forward. And now we can be thinking about, at least at a high level, what is the ARM memory system overview, and what are the things that it leverages. So ARM provides a versatile virtual memory system architecture that can be tailored to the needs of the embedded system designer. So what Stalling talks about a lot is he talks about the ARM being used for the embedded market. It's now kind of transferred over that I mentioned I have a Surface that has an ARM processor. Anyone who has a new Mac, it also has an ARM processor. And so it's actually started to go beyond that, but it's, you have like these levels of architecture. So maybe it falls into the ARM camp, but there's more to it. You can have a more capable ARM processor versus for an embedded system, you're going to have a lot lower kind of thing that's going to be used. They have virtual memory address translation. And so you can have a super sections, that's optional. You can have sections, large pages and small pages. So we see the same pages that we saw before with the, we talked in general and a little bit about what the x86 architecture does. Here is an illustration of the ARM virtual memory address translation for small pages. There's a single level 1 L1 page table. So maybe that will be one of the takeaways, that you're seeing at various places these caches, these buffers that are used for improving memory management, that the operating system is the kingpin for helping us out with that. To get a better understanding of the ARM memory management scheme, we consider the key formats as shown here. The control bits shown in the figure are defined in the table here. And so we can go back and forth between these to get a sense of how this would work. Remember, with an ARM architecture, that's 32 bits long. The ARM64, I think, is 64 bits, but it's anyway, everything is the same length in terms of how things are formatted. So we covered a lot of ground there, but let me just come back and summarize. So now we got a context in terms of computer architecture, what the operating system is doing, what of its objectives and functions. It is the whatever term you want to be using. I used first lieutenants in the past for sub-processes that the CPU leverages. Well, kind of like a whole different domain is now you want to keep things flowing. So maybe it's yet another type, but a different type of lieutenant, first lieutenant, that's scheduling and making sure that all of the resources are being used effectively. There's various types of scheduling that actually are used. And so long-term, medium-term, and short-term may be another example of using a methodological approach with the L1, L2, L3 type of cache. We talked about these various types of ways of doing memory management: swapping, partitioning, paging, virtual memory, using that TLB, the transition look aside buffer, and segmentation. All of these are within your toolbox that you can be using to improve memory performance. So the x86 Intel architecture, it uses address spaces, segmentation, and pages. For the ARM memory management, it uses virtual memory addresses, virtual memory management formats, and access control. So there are some differences between those two that we'll get a chance to be thinking about. So any comments or questions?
For the access control, can you like mess around with that as a user, or is that just strictly the person who created it?
Yeah, I skipped over that chart, but let me go over that. So for an ARM architecture, the AP access control bits in each table entry control access to the region of memory by a given process. And so a region of memory can be designated as a no access read only or write only. Furthermore, the region can be designated as privilege access only, reserved for the use by the OS and not by applications. And so these are the kind of things that we're starting to see with that access control. So basically, maybe you could say like the search space that you have available to you is reduced because each of these are designated. And so maybe a pre-filter for when you start to access memory, you can say, well, all of this is allocated for this function versus that. So that's a good question, David. Does that help give you some perspective on that?
Thank you.
Any other comments or questions? So maybe I'll check in on our remote folks here. Any comments or questions from folks? Did that pace fit your liking? You guys can reach out and let me know. Avery was kind enough to point out a couple of issues with the quizzes. And so one of them, there was an error. I was mentioning Avery before we started. I actually have to manually code all these quizzes. My personal strategy is I like to have it in Canvas rather than having you to be forced to pay for external resources. So it puts more work on me, but it also gives that potential for making a mechanical error. So I fixed that one. And Avery also mentioned that there were a couple of quizzes that did not have unlimited attempts. And so I'm going to fix that as well. So if you do find things like that, I would be glad to make those changes. I'll also be happy to give you full credit on the quiz And as always, I like to stay engaged with you guys. And so some of you have reached out to me on an individual basis. I'm here at 8 o'clock. And so I am an early bird, but also the drive kind of makes it, I would rather be here a few hours early rather than have to deal with traffic as bad as it can be. So just let me know how I can be helping you to succeed and master this information as best what works for you. There are different learning styles. And so I'm trying to be agile towards a lot of different learning styles. And so Tuesdays and Thursdays are architected different. So maybe that's one way to be helping on that front. But I'll go ahead and pause there and see if there's any comments or questions that people have. Anything else? Enzo, anything? Oates? Any questions? Thumbs up for Riley? Any comments or questions?
I'm good.
Okay. Ryan, any comments or questions?
No, sir.
Okay. And Samuel, any comments or questions? Okay. Well, anyway, it's good to see you all. I'll go ahead and end the lecture there. I'll stay around here if anybody wants to chat a little bit one-on-one. So thank you very much. Keep letting me know what's working, if this is helping you guys. Okay. All right. God bless now.